you're struggling with NMR, stick around. I have a great practice problem for you. This was sent in by a viewer, and this is something that you need to get right, because once people start to struggle with NMR, they kind of just give up if they don't learn it. So let's learn it right now so you can get this right on your exam when you see something like this. So like I said, this was sent in by a viewer. I'm going to overlay the thing they sent in real quick. All right, take a look at that. I tried to recreate it here with my terrible art skills. But this is what we have. We have this chemical formula of C7H5NO4. We have this spectra for proton NMR with integrations of 1, 1, 2, and 1 with what I kind of had to guess were their multiplicities because the resolution was not very great. My guess is taking on a really low resolution NMR. So first thing we do, what do? We got to figure out our degrees of unsaturation with our chemical formula, which remember it's 2C plus 2 plus number of nitrogens minus how many protons minus however many halides we have. So for us, it would be 2C, so what? 14 plus 2 plus 1 nitrogen minus what, 5 hydrogens. So we'd get what? 17 minus 5 is 12, and then, oh, I'm sorry, this is all divided by 2 as well. So slash 2, parentheses, PEMDAS. So we would get what? 12, I said, minus, or divided by 2, which equals, we have 6 degrees of unsaturation. All right, that's a lot we got to figure out, but we got this, don't worry. Now, let me look at our spectra. We have at minimum 4 distinct signals. I'm going to be honest, this one, I couldn't tell if it was 2 signals overlapping or not because of the resolution. So we're going to operate that it's a doublet for right now, but it might end up being 2 signals. Right here, this one single peak around 12, that is characteristic of a carboxylic acid. And I'm surprised it's really even that sharp. They must have had a great solid sample because usually they're really broad like this because they're rapidly exchanging. So we know we have a carboxylic acid. So let's draw that right now. Coming to something. Now we have to come up, that's minus 1 degree of unsaturation. We have 5 more. Okay, so how can we get rid of some degrees of unsaturation? And because we can look at the area where these are really downfield. Okay, so my guess, and because of their resolution, because they also had some kind of sub-splitting as well in those signals, my guess is these are aromatic protons. So I'm going to throw a benzene ring on there for right now. We're going to go to benzoic acid. And that will use up 4 degrees of unsaturation. So we have 1 more left that we got to use up somewhere. And with that, how many carbons have we used? We used 1 and then 6. So that's our 7 carbons right there. So we're on track for that. And we have 1, and then 1, 2, 3, 4, 5. We have 6 protons right now. So we need to get rid of 1, but we also need to use an NO2, which NO2, okay, so we have a nitro group somewhere. And that would also use up our extra degree of unsaturation. Because remember, a nitro group is N minus, like that. Okay, and then it's rapidly, it's resonating. So now we just got to figure out where we put in this nitro group relative to our carboxylic acid. So we have this singlet there. We have one pretty downfield proton. That was definitely a singlet. We have one that's a triplet, and then we have one that's like sort of a doublet, or it's maybe 2 signals. So if we have one singlet, we need to isolate one of these protons. So I'm gonna put our nitro group there. Now let's see, so we have our singlet, that's right down, and then it has these 2 electron withdrawing groups, really throwing it downfield. We'd get a triplet from this guy right here, a couple here. That'd be roughly similar J values. And then I'm really starting to think that, yeah, this is actually 2 signals just almost overlapping, and that gives us that integration of 2. And that gives us our thing. So I'm gonna assign 1, A, B, C, D, E. So this is A, B, and then this would be C and E. Coin flip as to which one is which, and then this one is D. See, that's how you dissect proton NMR.